and there are the various kinds of tags that are available, the passive tags, active tags, and hybrid tags, and also how a reader communicates with the tag and how a reader reads the signal, the data that is stored in the tag, and how the data is processed. So basic block diagrams have also been said, have also been shown to you, and I have also elaborated about the workflow of the tags and the readers, and also the various mechanisms in which the by which the reader can read a tag in the near field and also in the far field. There are basically these two types of ranges, and also why RFID is so much advantageous over other auto ID procedures, that has also been discussed. So today what I will do is that first is the RFID controller. That means, see, after the reader is reading a data, then the data has to be processed and accordingly some command has to be given. So that thing is given by the controller. If you remember the first diagram that I have shown you in the previous lecture, that is, there is a tag, interrogation zone, there is a reader, and reader is connected to a computer. So that computer is the commanding master who will be telling you what to do after the reader will be feeding the data from the tag to the computer. For example, in a toll tag, whenever a reader is reading a tag, for example, in the tag, whatever the information is given, there is no, the reader can says that there is no money that can be deducted. So when that data is sent to the controller, then controller will give out another signal which will tell the traffic signal, the traffic master server, that this vehicle with this registration number has not paid the toll tax, you please take care of that. So controller is the actual mastermind of this entire RFID tax system, RFID system. Now there is a middleware. The middleware, what does it do? It is a kind of router which is routing the data between the from the reader to the controller. Now, why a middleware is very much important? Because see, a is a very expensive device. Now, suppose there is a toll tax station. Okay, so suppose there are 5 lanes through which car can move. Now, for each of the 5 lanes, there will be 5 readers. Now, for each of the reader, if there is one controller separately, then it will be an expensive thing, and also it will be a loss of bandwidth, a loss of memory space also, because a controller comes with a huge amount of memory. So what we can do is that we can set up middleware software for each reader, dedicated middleware software. Now each middleware software will be taking the data from the reader and it will be sending to a base station controller, where the controller will be one which will be reading the data from 5 readers through the middleware. That is so much important, because middleware's only job is to take the data from the modulated data from the reader, to demodulate the data, to do some signal processing and send the binary data bit to the controller. Okay, so what happens, so for this technique I need very small amount of memory, very small amount of architecture. I don't need a I don't need an expensive workstation. So with a simple microcontroller chip also I can do this thing. So middleware, if I set each middleware for each dedicated middleware for each reader, then my the entire system's expense comes down, and also the intricacy of joining every reader also comes down. Now, the third aspect is the security of RFID system, because you know that there are many spying which is going on. So we will be talking about the security of RFID systems, how third party can attack RFID reader or tag, and what can be done to combat that. And after that, RFID applications which will be solely based on vehicle management, the electronic toll collection, vehicle speed detection, proximity detection, and vehicle to vehicle communication. Vehicle to vehicle communication means, see, as concepts of smart cities and Internet of Things are coming in the modern generation. So vehicle to vehicle communication means what? That suppose there is a crossing of 4 roads. Okay, so if I am driving through one road, then the entire traffic condition of all the other three roads should be visible to me. Okay, and the same thing, my traffic condition, my position should also be visible to the other cars which are in the other three crossing junctions. So that is vehicle to vehicle communication. I'll elaborate on that later. So as I've told you, controller, it is nothing but the brain of the RFID system. And actually what happens, I will just discuss it with the example of a toll tax. Suppose a car which is going, okay, so there is a RFID tag on the car, and the reader will read the tag, and through the middleware the information will be fed to the controller. Now there are two things: either the controller will see that the money is deducted, or the money is not deducted due to the insufficient balance. Okay, so what the it will send an alert to the RFID tag to through the reader that you have not paid your this thing, your money, and you are given this much time to pay the to clear the due. And the same thing, the same information will be conveyed to the traffic, and there will be a door through which that car will be passing, and the data of the car will be stored in the inventory of the controller. So suppose in a minute around 10 cars are passing through a lane. So for each of the 10 cars, the information is getting retrieved and it is stored by the RFID controller, the inventory, so that if there is discrepancy for any kind of for any car, then directly the traffic police server can access the RFID controller and can retrieve that information from that for that car. Okay, and this is one also very important, because suppose if there is any mishap which is created by the driver somewhere, so if I know the last location, then by accessing the controller of the RFID, I can track down the car. At least I can get all the details of the car. Now comes the middleware. So as I've is nothing but it's a kind of router which will be routing the data from the reader to the your this controller. So the first thing is data collection. Now middleware, what will it do? There are two kinds of middlewares. First is that I can group, suppose three readers at a time. Three readers will be accessing one middleware, or one reader per middleware. Now if there are many readers in one place, then I can group it in such a way that three readers will be accessing one middleware. So for each reader, the middleware will collect the data, and what it will do is that, see, the data that will be collected by the middleware is the data that is directly captured by the reader from the tag. So the data will be contaminated by noise. So one function of the middleware is to remove the noise, to smoothen the signal, then it will demodulate the signal, and then it will extract the after demodulating, what will happen, it will get the baseband signal, and that baseband signal will be, and from that baseband signal the binary data will be collected and it will be fed to the control. So that is data collection. Data routing also, because why I am saying data routing, because it is integrating the RFID networks and it is routing each of the data from each of the reader to the controller. Process management. Now this is not actually relevant to the transport system. It is in general, process management is there for middlewares for RFID systems. These are used in industry systems where this middleware, I can program the middleware to initiate some function for the readers. Suppose one middleware is connected to three readers, so middleware I can program it and I can send one command through the middleware to the readers, and that same command will be transmitted by the readers to the respective tags. So that is known as process management. That is not actually relevant to your vehicle management, but this function is there. And then device management. Device management is what? That middleware will be monitoring the readers. That means if any reader is unable to capture the data from the tags, then that information will be that information will be retrieved by the middleware, and accordingly it will be fed to the controller, and then the controller will be sending the same thing to the user. That is one part. Second part is that it will coordinate among the readers, and one more important thing of device management is that the middleware is programmed in such a way that it can accommodate some extra readers also in its network. So that is also a part of device management. That three readers accessing one middleware. Now suppose a fourth reader is required to be added in the network. So that provision is also there in the middleware. So these are the architectural layers of the middleware. As you can see, the basic layer is the reader interface. Now you know, because as the name suggests, reader interface means it is taking the data from the reader. So that is what is the reader interface. It is the lowest layer because the data is first accessed by the middleware from the reader, and that is why this is the lowest level. And then comes the data processor and storage. As I have told you that after the data is getting retrieved from the reader, the middleware will be responsible for processing the data. Processing means it will be smoothing the signal, the modulated signal by removing the contaminated noise, and for that it employs mashed filter technique, and then there will be demodulation, and from after that after demodulation you will get some binary pulse data, and from that pulse that binary data will be extracted, and then it will be given to the application interface. Interface means the interface between the middleware and the controller. So it will communicate this data to the application interface, and it will give the access to the application interface to further process the data to either to store it in its inventory or to give some suitable command to the reader via the middleware, and so. And then the middleware management layer. The middleware management layer, it helps in managing the configuration of the RFID middleware, because sometimes because let me give you one example. So suppose the middleware is configured in such a way that it will be able to read, it will be able to sense, and it will be able to retrieve the data of 3 readers. Now suppose I want one more reader to be included in the network. So that thing is done by the middleware management. The middleware management is nothing, it is comprised of an FPGA circuit, which is now the basic essence of FPGA circuit is that I don't have to change the circuit again and again as per the network requirement. I have one circuit. Suppose the circuit is given with the provision of 10 readers to be accommodated. I have that circuit, and I just need to program the circuit to accommodate readers up to say 10 number of readers, like that. So that is the middleware management. So middleware management comprises of an FPGA. Why FPGA? Because it is not required to be changed every time whenever the network requires modification. Only some programming of the FPGA will be done, and then the network I can accommodate some new device to the network. Now this is one example of RFID middleware. It has been developed in the University of California. So see, the lowest level is the RFID hardware, from where the middleware will be retrieving the data. So it will be this RFID hardware means it is obviously the readers, because the middleware will be interfacing the reader with the controller. So it will be taking the data from the reader, and readers are, as I have told you in the previous slides, in the previous lecture, that there are 3 kinds of readers: stationary, mobile, and cluster readers. So for all the kinds of readers, this thing will act. And then comes the protocol layer, because as you know that suppose for vehicle management you have a 2.4.8 gigahertz range. Okay, now for seashore communication you have ultra high frequency range in megahertz range. So for each of the frequency ranges there are different protocols of data transmission. Okay, now why this protocol layer is added, it may happen that one middleware is accessed by one reader which is acting in the gigahertz range, and another reader which is acting in the megahertz range. So the protocol should be different for each of them. Otherwise, there will be contamination of data. There will be overlapping of data. There is aliasing of data. Okay, and if there is aliasing of data, then what will happen? The waveform will be disrupted, and the wave and the signal that will be captured by the controller, that will be fed to the controller, will be contaminated by suppose the data which is fed to the controller of the gigahertz system, it will be not a pure data, but it will be contaminated by the data of the megahertz signal. Okay, so that is why different protocols are there. For UHF, for ultra high frequency, there are certain protocols. For high frequency, there are certain protocols. For gigahertz frequency, there are certain protocols. So according to the protocol, the data structure, the data layer will be structured, and the data packets will be formed, and it will be sent. And then comes the data management, as I have been telling you in this slide, data processor and storage. So here comes the data management. So data management means what? As it is written, it will verify the data which is coming from the reader. Suppose there are three readers which are connected. Now the middleware is responsible to, and suppose all the three readers are sending data at a time. So the middleware is responsible to separate each of the data. Okay, so which reader is sending which data, and that thing is done by some demultiplexers, digital demultiplexers, and then there is a filter to filter out the out of band noise. Then there are smoothing curves, matched filters to reduce the effect of noise, and then there is a cache memory, and then is transformation. Transformation is nothing. It the demodulation part. So after demodulation, the raw data that it will be that we will be getting, it will be sent to the XML framework. Now, as per now in the XML framework, it will decide what kind of data it is. Okay. It may be, suppose for some kind of consignments, it is kind of say Excel data. Okay, so like that. So case to case, the data type will be vary. Okay, so the middleware has to decide what is the data in the XML framework, and according to that, the data will be presented to the controller. That is the highest level, that is the middleware to controller interface or the application interface. So over there the data is presented. So this is generally the 5-layer structure of the middleware which is followed. Now the security of RFID systems. Now attacks can be carried out for reasons, and it can be grouped into types. Okay, so first is spying out. Spying out means what? The attacker is trying to get unauthorized access of information and data to the active and passive file. For example, suppose a controller is there. Suppose a toll tax controller is there. Okay, let me take an example of a toll tax. Suppose a toll tax controller is there. It is connected to say 10 RFID readers through middleware, and thousands of cars are passing through in a day. Lakhs of cars are passing in a busy toll tax region. Okay, now for each of the lakhs of cars, the cars or lorries or buses, the money is deducted, and the information of the deducted money will be kept to the in the controller. Okay, now if any attacker gets unauthorized access to that controller, then what can he do? He can route the entire financial transaction to his account. So you see, lakhs of transactions that are going on in a day. If the controller is prone to such spyware, then what will happen? Each of the transaction will be credited to the spying account. So that is a very dangerous thing, and generally that thing is combated by using some. That is why the cryptographic part is coming into account. That I told you in the previous lecture, the previous discussion, that in the reader chipset, there is one controlling unit which will be responsible for the cryptography part of the signal. Now, once the cryptography is done, then whatever the data that will be fed by the middleware to the controller, it is an encrypted data. So a spyware cannot detect that encrypted data until and unless it has the key of the data. Okay. The second is the deception. Deception is with the RFID tags. Now, suppose I am a driver. I am going through the through the toll tax. Now, if I can modify the tag in such a way that even if I don't have balance, it will show that I am having balance. Okay, and it will be giving out some false debited statement case. So that is known as deception. Deception means giving out false signal. Okay, so or I can tell you a better example is a speed detection case. Now, suppose the speed limit is 30 km per hour. So whenever a car is entering in that zone, the reader will be sending to the tag the comment that your speed should come down to 30 km per hour, and the communication is going on in both the ways. And there is a sensor which will be sensing that thing, and it will be directing the actuators which are connected to the throttle and the brake to reduce the speed. Now, if somehow the tag is the tag is designed in such a way, tag is tampered in such a way that say at 40 km per hour, the tag is giving out such a signal that the reader is reading that signal at 30 km per hour. And then the reader is saying that, okay, you have reached the 30 km limit, now you can and go. So the sensor is not getting any more signal from that. So that is known as deception. That means the feeding wrong information to the reader from the tag. And the third is denial of service. That means the kind of attack which affects the availability of functions of the RFID system. Suppose the reader of the speed breaker, if it is tampered in such a way that it will not be able to control the speed of any car. So that is known as the denial of service. That means the service for which the RFID is adopted, that service is failing. Suppose for toll tax also, if the reader is tampered in such a way, or if the controller is tampered in such a way, even denial of service means the middleware may also be tampered in such a way that the reader will not be able to retrieve the data of the tag for deduction of money while the card is passing through the under the reader antenna. So that is known as the denial of service. Attacks on the transponder means it is solely concentrated to the tag part. First is the permanent destruction of the transponder or the permanent destruction of the tag. The first thing is tag. One of the things important things of a tag is a antenna which is incorporated along with the semiconductor chip. So it may happen that antenna is severely damaged or cut off. Severely damaged. Now if the antenna is designed for 2.4 gigahertz response, it will not be able to capture signal at 2.4 gigahertz. So the tag is damaged, the reader cannot detect the tag, and hence the reader cannot control the vehicle which is having the tampered tag. Second thing is known as transponder shielding or tuning. It means the tag, everything is intact in the tag, but still the reader will not be able to detect the tag. Why? Because we know that if there is a metal surface, anything which is metallic, and if it is put in the at the vicinity of an antenna, then the antenna radiation which the antenna radiation is affected very much. That is one thing. Second thing is that if I shield the tag with any metallic object, now what is a metal actually? Metal is a perfect reflector of electromagnetic waves. So if I shield that tag with some metallic object, what will happen? The electromagnetic wave that is given by that is directed by the reader to the tag, it will be directly reflected to the reader without reaching the tag. So what is happening? The tag is shielded from the reader. So that is why the reader will not be able to read the tag, and the transponder can bypass the monitoring of the reader. So these are the kinds of attacks that can happen. Now, to combat these kinds of attacks, what happens? There is a connector in the chip, the semiconductor chip, that whenever there is some tampering in the antenna, then the chip will be sending out a signal, an omnidirectional signal that tampering has been done, and it is not, because the chip is designed to work on 2.45 gigahertz. Now, say the antenna is tampered in such a way, even if it is tampered, it will be able to capture some signal. It may not be 2.45 signal, it may be 12.45 gigahertz signal. So whenever it will be catching that, now that is a rubbish signal. Now whenever it will be catching that 12.45 gigahertz of signal, the semiconductor chip will be sending out the information that I'm capturing 12.45 gigahertz of signal, and then it will be alerted. Okay. And now the attack on the RF interface. There are two kinds of interface. One is the middleware to reader interface, and the second is the middleware to application layer of the controller interface. Okay. So interception of the communication between reader and transponder, that may happen. And another interface is obviously the reader to tag interface. So whatever the communication which is going on between the reader and the tag, it may be eavesdropped by some third party. That is why cryptography again becomes very much important. Second is, suppose vehicle to vehicle communication scenario, where for any vehicle in any crossing, the condition of the traffic of other vehicles in other crossings is fed. Now, if anyone wants that no one in that four road crossing should get any information of each other, and I will disrupt the traffic, then what will he do? He'll just use a jamming signal. What is a jamming signal? A jamming signal means a very high, a very spike signal or an impulse signal. Okay, so whenever the impulse signal will be generated, it will overwhelm the tag signal in such a way that the reader who will be reading the tags, the reader will be receiving signal which will be detected only as noise. So that is the essence of a jamming signal. Whenever a jamming signal is there within an environment, what does it do? Even suppose the communication is going on at 2 to 5 gigahertz. So within 2 to 5 gigahertz, if I can create a jamming signal or if I can create a spike, then what will happen? Whatever the signal that will be fed to the reader from different kinds of tags will be just a noise signal within that range of 2 to 5 gigahertz. So what will the reader see? The reader will see that okay, I am getting a noise signal. That means there is no traffic in. Let me sit idle. Let me not give any instruction to any of the other tags. So as a result, what will happen? None of the cards will be able to get the traffic condition of other roads. Okay, so that is known as interruption of the communication between reader and the transponder through jamming. Third is modifying the read range in order to be being able to scheme a remote transponder. Now what happens if there is a person who is driving a car, if he does not, suppose he does not want to give toll to the particular toll station. Now a reader and a transponder, the reader and the tag, they are working in a definite read range. As I've given you the formula from the Friis transmission equation, they are working in a certain read range. Okay, now the tag can be modified, may be modified in such a way that the read range will be reduced. Now suppose the read range of the original tag to reader is say 5 meter. Now if the read range is reduced to 3 meter, then when the car is passing through the toll tag, the distance between the tag to the reader is 5 meter, but the reading distance is reduced to 3 meter. That means what is happening? The reader is not being able to read the tag, and the tag can say, and the car can safely move out without giving any tags. And fourth is the blocking a reader with DOS attacks. Now RFID application. Now the first part is a very general thing, and second part which I want to discuss is that developing RFID vehicle tracking systems. It has its challenges. Okay, first challenge is that it has to read moving tags. You see, for any other auto ID procedures. Acha, can all of you hear me?
Yes, sir.
Yes, sir, you are clearly audible. Yes.
Okay, okay. Okay. So one of the challenges of RFID design is that it has to read the tags while the car is moving. The car may be moving at 60 km per hour, it may be moving at 20 km per hour. Okay, so the reading time is very short, and it is the main difference between RFID tags and other auto ID procedures. Because if you see a barcode which is read by a laser, you will see that the barcode is held still and the laser is reading that barcode. When you are using a smart card, what you are doing? You are swiping the smart card through a slot, and it is getting enough time to read the data within the in the magnetic chip of the smart card. So each of them are getting enough time to read, but the reader and the tag interaction time for the RFID cases in vehicle management is very less. This is one thing, and this is a very challenging part. And the second challenging part is designing tags on metal vehicles, because as you know, as I've told you, that metals are very good reflectors of electromagnetic waves. So whenever a reader signal is impinging on the tag, a part of the reader signal will be impinging on the roof of the vehicle also. The roof of the vehicle is metallic. Now the electromagnetic wave will be back radiated from the roof of the wave to the tag, and then that will create a destructive superposition, with the radiated field of the tag antenna. And as a result of which, what will happen? The data which is stored in the tag, it will be wrongly transmitted to the reader. So one of the design criterion of RFID tags is that I should be giving a metallic shield underneath the tag antenna, so that what will happen, whenever the back radiated wave will be trying to reach the tag antenna, it will first encounter the metallic shield. Now again, so whenever it will be encountering the metallic shield, it will reflect back the electromagnetic wave to the car roof. Okay, so it will not let the reflected electromagnetic wave from the roof of the car to hinder the radiated wave of the tag. Okay, and how to deal with this very fast moving tags, how to deal with this short introduction time. As I have told you, there are two design criteria of RFID antennas. First one is that the reader should be circularly polarized. Second is that the tag should be omnidirectional. Here comes the essence of why a reader should be circularly polarized. Suppose the reader is being able to read the signal if the electric field comes at 30-degree angle with respect to reader. Suppose the scenario is like that, then what will happen if the car moves at a very high speed, then that 30-degree then the radiated field at 30-degree angle will be, say, at 0.05 microsecond, which will be not enough for the reader to retrieve the data. But if it is circularly polarized antenna, circularly polarized means what? It will be able to sense the data, it will be able to sense the electric field from any direction. So, suppose the read range is 5 meter, then, and if you take the reader to be at the center, then from 2.5 meter left of the reader to 2.5 meter to the, 5 meter to the left of the reader to 5 meter to the right of the reader, in this entire range when the car will be moving, the reader will be able to sense the tag, because in this case the orientation of the electric field with respect to the reader is not a matter of concern, since it is circularly polarized. So an antenna, a car will be taking some time to cross that 10-meter distance, so it will be giving some time for the reader to interact with the tag. So that is why circular polarization is that much important. Now here comes the electronic traffic control. This is the basic flow of the electronic traffic control. Now the tag which is given to the vehicle owner, it will be having all the information of insurance, registration number and all the things, and the bank details, and it will be linked to the bank account, and it can be charged by, by any simple procedures, the account. So what happens, first the card enters the access point, from where the reader is able to sense the tag. Okay, then the reader reads the RFID info, it reads the password also. Password means the unique number of that vehicle, and then it says that whether that unique number is authenticated and validated by the transport department. If it is no, then it is no action, that means it is a false thing which is moving. If it is yes, then then the reader senses that, then the middleware senses that, okay, it is a car or a bus or a truck, whatever is reading, because I'm getting an authentication and validation signal, authentication and validation code, which is verified by the transport department. And then what happens, you may keep a door, the door will unlock, and whenever the door will be unlocked, whenever the car will be passing through the door, there will be another RFID reader which will be retrieving the data, the entire data of the car. You may keep that RFID reader within that door, or you may keep the RFID reader in that same position where it will be authenticating and validating the card. Okay, you can keep it over there also, or you can keep two readers also. Why I keep two readers? Because authentication and validation, it requires a different database which is fed to the RFID reader through the middleware by the transport department. That means this reader is having a dedicated function of matching the unique code of the card with the transport department database. Now, along with that, if the reader also needs to retrieve the data of the tag and store it and do the banking transactions, then it will require some more memory. And as you know that RFID tag comes with maximum of 64 kilobyte of memory, so it may not be possible for, because in city cases the database of vehicles is very high, so it may not be possible for one reader to undergo both the processes. So that is why the processes are divided among two readers, and both the readers will be connected to a single middleware. Okay, keep this thing in mind. Both the readers should be connected to a single middleware which is joined to some controller. Okay, so that is why there are two readers. One will be reading the password and it will be matching it with the database of the transport server, that whether it is a registered car or not. And the second one, which is in the door unlock, which is at the door of the uh, toll tax, this thing will retrieve the information of the car, along with it will do the banking transaction. Okay, and from there it will go to the database. So this is the same thing which is given over here. Now we are coming up with fast tag systems. Okay, so if you see the fast tag system, there is one QR code and there is this tag antenna over here. Okay, and the gap that you can see within the tag antenna, it is the semiconductor chipset. And if you can see minutely, within the gap there are two protruding arms. One is going up and another is going down. These are nothing but these are compensating the inductive impedance of the chipset. This is a capacitive loading over here, because in general the chipset which is introduced in a tag is having some inductive impedance, and these protruding arms are balancing that inductive impedance with that amount of capacitive impedance. The anti-tag collision method. This is one thing, that if more than one tags appear at the same time to the reader, then what will happen? The reader must not confuse two tags. The reader should be able to sense the two tags separately. Okay, so because if the reader gets confused with the two tags, then it will be difficult. Even if two cards come at a time, the reader should be able to read the two cards at a time. Now you can say that in a electronic traffic control, in an electronic toll tax collection, you can make a lane such a way that one car can move at a time. But if you come to the speed braking system, then what will happen? You cannot keep one speed breaker for each of the lanes. Over there, one speed breaker will be serving all the lanes. Suppose there are three lanes, so one speed breaker will be serving all the three lanes. Suppose the speed breaker is having a range of 5 meters, so say 10 meters. So within that 10-meter range, whatever will be the cars, all the cars, tags of the cars will be able to communicate with the reader, and accordingly the speed should be decreased to 30 km per hour step by step. So the reader should be able to sense each of the tags separately. That is one of the main reasons. That is the anti-tag collision method over there. One thing that happens is that image processing, that along with that RFID identification system, there is an image processing block where the RFID, there is a camera which is fitted, which can see all the cars within its range, and with that image processing system it will be verifying the RFID system, and then it will be able to understand that which car from which car a particular tag information is coming. This is one way, but as I have told you that any block which is employing a visual signal processing, it requires a lot of memory, either video or your image. Video will be using more memory, but image also uses a sufficient amount of memory. So video capture or image capture is not a very intelligent method. Then what we do nowadays is that we use a GPS module along with the sensor. So the GPS module will accurately tell me what are the positions of the cars, and by using a software we can understand that from which position which tag information is coming, and then the reader can identify the separate paths of the tag signals. Okay, so I can integrate a GPS model with the RFID reader. Now comes the speed estimation. As I've told you that in a speed breaker there will be a reader which will be able to communicate with the different cars which are coming, and accordingly it will be able to control the speed of the car. So first thing, before controlling the speed of the car, what the reader has to sense is the speed at which the car is moving. If it is not able to sense the speed at which the car is moving, it will be not able to give the exact information to the sensor what to do. For example, suppose the car is moving at 60 km per hour and it is entering the reading zone of the speed breaker reader. Now the threshold signal is 30 km per hour. Now if the car is at 60 km per hour, then it is quite high. Then it's about 30 km per hour higher than the threshold level. So the signal, the actuator signal that will be given out by the comparator, it should be a higher voltage compared to a car which is moving at 40 km per hour, because a car which is moving at 40 km per hour is quite close to the threshold. So the actuator signal which will be given out by the comparator, it will be less. That means when the car is moving at 40 km per hour, the comparator set will be giving out a 5-volt signal to the actuator. Accordingly, automatically apply. Now, if the car is moving at 60 km per hour, since the comparator will be sensing a wide difference in the actual speed and the threshold speed, say it will be giving out a signal of 15 volt, and accordingly the brakes will be pushed. Okay, so the first thing is that speed estimation. That is very much important. And over here, generally we use, as you know, that a car vehicle management, we use the range of 2.4 to 5.8 gigahertz. So since it is a gigahertz range, as I've told you, it will be working the far field region. So it will be, so the tag which will be read, it will be the backscattered signal, not the induced field. Okay, so what will happen, you see, there is a transmitting antenna and the receiving antenna. So the transmitting antenna will be sending the signal, and the receiving antenna will be and it will be hitting the tag, and the tag will be backscatter that signal to the receiving antenna. And then by using the Doppler method, I will be able to sense the speed of the car. Now I'll come to the Doppler method. Now this is just a software peripheral which is used for detecting the speed, and this is a transmitter state diagram of the software. First it will be idle, then after a certain time it will send out a query, and if it does not get a backscatter signal, then it will again go to idle state, and if it gets the backscatter signal, then it will acknowledge it, and then it will work, and again then it will go to the idle state. Now come to the speed estimation part. This is a very important part. See, the reader range is from this point of the triangle to this point. That means you see one point is marked as position to receive first valid EPC. That means this is the entry point from where the tag of the card can be read by the reader antenna. And this is the last point. This is the last point where the tag of the antenna can be sensed. So after that point, the tag of the antenna cannot be sensed by the reader. The tag cannot be read by the reader antenna. Okay. So when the car will be moving from this direction to this direction, you see there will be a change in relative velocity, because in this direction, what will be the relative velocity with respect to the this antenna? If I do it in the, suppose if I take the horizontal position, say if I take the horizontal position, so if it is moving in the v, if it is moving in direction, so suppose the antenna, it is, you take this horizontal plane. Okay, so the what is the component of horizontal component of the speed? Then v cos theta is, over here it will be v cos theta, and over here it will be v cos theta e. So the relative speed between the reader and the car is changing as per the angular separation. So as the relative speed will change, there will be a Doppler shift. The frequency shift is given by delta f is equal to 2v cos theta by c into fc. Okay, and then by measuring this Doppler shift, what will, here comes the middleware part. The reader will just sense the relative speed between the car and the reader. It will do nothing else. Okay, after sensing this thing, it will send this data to the middleware. Now this data will be sent to the middleware by some modulation technique and so on. The middleware, what it will do, it will demodulate the signal, it will remove the noise contamination of the signal, and then it will send the signal to the controller. The controller will be performing this Doppler shift calculation, and it will calculate the speed of the vehicle. Now then what it will do, suppose the speed breaker is at 30 km per hour. After sensing the speed of the vehicle, if it sees that the speed is above 30 km per hour, it will instruct the middleware to send the signal to the reader that now it should send a signal to the tag to activate the sensors for speed control. And if it sees that the speed is below 30 km per hour, it will send the signal to the middleware instructing to say to the reader that no action is required. So try to understand the workflow. What the reader is doing, the reader is just sensing the relative speed. It is doing nothing else. Reader is just sensing the relative speed and it is sending that data to the middleware. The middleware is removing the noise, downsampling the signal, demodulating the signal, and feeding the raw data to the controller. The controller is then performing this calculation in its programming, and it is seeing whether it is above the threshold speed level or below the threshold speed level. If it is above the threshold speed, then what it will do? It will instruct the reader via the middleware to send an instruction to the tag that now you activate your sensors for speed control. And if it is below the threshold, then the controller will say to the reader via the middleware that no action is required, so no sensor is required to be activated. So this is the workflow. Now this is the sensor based this thing RFID system. Yeah, yeah. This one is a better picture to discuss. Sorry for the interruption. Is the screen visible properly?
Yes, sir, we can see.
Okay, okay. So now here this is the basic block diagram of the speed control system. So this is the reader part. Okay, it is giving the this is the reader part. Now there is a sensor which is attached to the wheel. Okay, this is a GPS antenna. Why a GPS module is integrated? Because GPS module gives an additional information of the exact location coordinate to the controller. Okay, so now what I have said that the controller will be calculating the uh,
Mumeji, there is no audio from your side.
Sir, you are not
Interesting.
audible, sir.
Okay, let me see.
Now it's okay, sir. Now it's okay. Okay.
Now it's audible.
Ah,
Okay, okay, okay. So keep this thing in mind that the comparator acts as a dynamic way. So that is why you don't use an op-amp comparator that we use in BTEC. So that is why the decision stage is given by the fuzzy logic based controller. Okay, so it is not an op-amp, it is a kind of controller which can dynamically set the voltage value to the speed level. According, so the controller will be able to make the decision that what should be the amount of voltage that will be given to the actuator such that the throttle and the pump brake will work to reduce the speed, because if it is moving at 60 km per hour, brake and throttle should be pushed at a higher force, by a higher force. That is why more voltage will be required. So that is why not a simple op amp is used in the decision stage. In the decision stage, a comparator is used, and the comparator is always communicating with the secondary PC, which is connected to the RFID sensors, and this secondary PC is resolving the amount, the voltage that the RFID sensors are sending. Okay, so the from that RFID sensor to the secondary PC, which is a controller, the Doppler shift is given to the middleware, which is over here. Okay, so now after getting the voltage information, after decoding the voltage information over here in the secondary PC, it will give it to the, through the router, it will give to the main PC. It has been given over here as a PC, but it is a high level microcontroller. Okay, so as per that value, it will give out a voltage to the throttle and the pump brake through this sensor. Okay, so this is the generally the decision stage. So decision stage and actuation stage. Now proximity detection. What is the proximity detection? Proximity detection means that you are driving a car. Okay. Now if another car comes to a dangerously close level to you, then both of you should be alerted. Your car and the driver who has come to the dangerously close level. Both of you should be alerted that both of you have come to a very close range, and you should take care of that. Because many times it happens that we cannot have a clear view through the rear wind mirror, or many things may happen, or a careless driver may be driving a car, he may come very close to the to another car which is moving forward. So I need a kind of proximity detection so that the drivers may be alerted. Okay, so for proximity detection, what we have, the tags have sensor tag technique, STs. Okay, what do STs do? STs decode the backscattered signal Estes decode the backscattered signal from the nearby tags with the reader. Okay, so the screen is visible.
Yes, sir. Yes, sir.
Okay, okay. So we use a sense attack technique, and which will decode the backscattered signal from the nearby tags and communicate with the reader. So let us go to this block diagram for better explanation. Here what happens that you see, this is a SPDT, that means single pole double throw switch. Okay. First, this antenna, suppose you are driving a car. This is the antenna, the tag antenna of your car. Okay, your tag antenna is continuously radiating some wave, right? So, and it is also getting some radiated waves from some tag antenna of the car, which has come very close to you. Okay, now when your antenna will be receiving the radiated wave from that tag antenna. No audio. Am I audible now?
Yes, sir. You are audible, sir.
Okay, because I got one message that there is no audio. Okay.
Sir, at 4 o'clock we can't hear you, sir. But now it is okay, sir.
Okay, okay, okay. So your antenna will be receiving some signal from the antenna of the card, which has come very close to you. Now when a signal, it will capture that signal and it will be giving to the matching network. Why the matching network? Because see, the other part is the chipset part. This envelope detector, comparator, state machine, this entire thing is in the semiconductor chipset. As I've told you that an antenna is interfaced with the semiconductor chipset through network. Otherwise there will be mismatch between the antenna impedance and the chipset impedance, and there will be huge reflected wave. Okay, so it will pass to the matching network to the envelope detector. Now, in general, due to this proximity calculation, since I am dealing with cards which are coming to the very close distance to each other, so I go for amplitude modulation. I don't go for frequency modulation or other thing, because amplitude modulation will be enough for this kind of signal, because here I'm not actually giving out some other information, other digital information. For example, in a toll tax, you are giving out some digital information about the registration number and so on. But here I'm not giving out any digital information. I'm just giving out information that how close I am. Okay. So for that thing, an amplitude modulation technique is much easier. So the demodulation of amplitude modulation is an envelope detection technique. Okay. So from that envelope detection, I will get the, after decoding that amplitude modulated signal, I will get the distance between my car and the other car. Okay, suppose the danger less distance is say 10 meter, say for example. Now your car, and that car from which your tag is receiving the signal, it has come to a distance of 5 meters. From envelope detector, you will decode that information that it is. So hysteresis comparator is a simple op-amp comparator. So this is 10 meters. So this is threshold is 10 meters. This is 5 meters. So it can say it is detecting that it has come to a close level, and then it will go to the digital section, state machine. Why it is a state machine? Why it is not just an analog signal directly giving to the SPDT switch? I mean, it may happen that okay, it has come to the 5-meter distance. Now just let me give an information, a digital in bit 1, and if the bit 1 is transmitted over here, then I can see it means that it has come to the dangerously close level. If it is more than 10 meter, then I can say that okay, it is above the proximity level, and so let me transmit a 0 state, and whenever the 0 state will come to the SPDT switch, then my tag will understand that it is beyond the proximity range and I am safe. But I'm not doing that. I'm using a digital section. It is a state machine, because if you remember the previous diagram, there are 3 parts. First part is that when it will be coming, suppose that 10 meter is the distance, whenever it will be coming within 8 meter, the driver will be alerted that you are going to the proximity range. When it will be coming to say 5 meter, then its brake will be starting to then its brake will be starting to actuate, and when it will be say 3 meter, then the entire speed control will be taken up automatically rather than manually. Then the driver will no more be able to control the speed. Okay, so that is why the state machine is required. So when suppose after envelope detection, it has seen that it has come to 8 meters. So threshold is 10 meter. Comparing it with 8 meters, say it is giving 2 volt. So 2 volt is mapped to just alert in the digital section. Say 2 volt is mapped to 1 1. So 1 1 0 1. 0 1 is what? 0 1 is only triggering alert. So whenever it is 0 1, according to it, SPDT will work, and then it will just alert the driver. That's it. Now suppose the after the envelope detection, the distance is the 4 meter. Threshold is 10 meter. Now the digital signal that is given out is, now suppose it is given out, it is giving out 5 volt. 5 volt is mapped to say 1 0 in the digital section. That means from 2 volt to 5 volt it is mapped to 1 0. That means whenever it will be more than 2 volt but less than 1 volt, that means it is 1 0, and 1 0 means what? Brake will be taking control. Okay, now suppose it is 3 meter over here in the comparator. Now say it is 7 volt. So in the state machine, what it is done, from 5 volt to 8 volt, it will be 1 1. 1 1 means what? It will be an automatic override, and it will override the manual control, and automatically the brakes and the throttles will come into action, and it will decrease the speed. So that is why it is known as a state machine. State machine is mapping the analog input of the comparator with the digital state. Keep this thing in mind. That there will be some range. Say from 2 volt to 5 volt, it will be 0 1. 0 1 means alert. 5 volt to 7 volt, it will be 1 0. 1 0 means brake will be taking over. 7 volt to say 9 volt, it means 1 1 state. 1 1 state means automatic override. Okay, so in this way the state machine is designed, and accordingly the tag will be instructed. Okay, and tag is connected to the sensor part, and then the sensor will be instructed accordingly. So that is why this digital state machine section is very much important. I cannot directly give out 0 when it is below threshold and 1 when just it is above threshold. Then the tag will not be able to understand that what to do. Okay, 1 means it is proximal. Proximal means how much proximal. If it is too dangerous, then it should be automatic override. It is okay, I'm going to a proximity range, then I will be alerted, then manually I will move away my car. Okay, so this distinct division should be there. So that is why this digital section is over there with state machine. Now, vehicle to vehicle communication. Before coming to this, I'll come over here. So, vehicle to vehicle communication, how it is done? A tag is connected to a GPS module, and a tag is also connected to a in-vehicle monitoring system. Okay, so now what happens if you look into, so this rectangle, big rectangle is of one car and this one is of another car. So here in vehicle to vehicle communication, there is one important thing that you have to understand is that along with the tag, within the vehicle there is a reader. It will be acting as a reader or it will be acting as a repeater. I'll tell you when it will act in which mode. So suppose it may happen that a car is moving in a straight way, in a linear fashion, rectilinear fashion. Now suddenly it wants to. Now another car is moving just behind it. Now if it doesn't give a signal that it is moving, it is going to take a right turn or a left turn. Then the car which is coming just back, following that car, then it may be some disturbance over there. Okay, so in that case what happens is that this in-vehicle monitoring system gives an instruction to the car, to the tag, that I'll be going to take a turn. That means whenever the vehicle will be trying to take a turn, the in-vehicle monitoring system, which is nothing but a sensor which is attached to the axle of the wheel, and whenever there will be a turn motion, torque will be generated, and that axle of the wheel will be giving out a sensing signal. Whenever that sensing signal will be sensed by the tag, and as the tag is having a GPS module, along with that, it will be sending out a signal which is given as P is equal to WC plus AXY. WC means what? Is a warning code. Warning code means what? I am taking a turn. So I am taking a turn. That warning code is 10. I'll be pushing a brake. That warning code is says 01, because suppose I am moving at 60 km per hour. The car which is following me is also moving at 60 km per hour. There is a safe distance. So suddenly, if I put a brake and I slow down my car for any reason, suppose I suddenly want to go down to 20 km per hour. So I can go down to 20 km per hour, no problem. But the car which is behind me is still moving at 60 km per hour. If the driver is not that much alert, then what will happen? He will directly hit my car at the back. So this IVMS, which is nothing but a system of sensors, it is the various sensors are connected to various points of the wheels and the throttle and so on. So whenever there will be a turn, the axle will be giving the sensor which is given at the which is put at the axle, that will be giving out an information to the tag that a turn will be taken. If you want to hit a brake, then the sensor at the brake will be giving out information to the brake will be pushed, and accordingly this warning code will be generated. Suppose for turning the warning code is 01, for brake the warning control is 10. If there are more controls, then the coding will be different. Suppose there are 8 controls, then the coding will be from 000 to 111. If there are 16 controls, then it will be 0000 to 1111 and so on. Okay, so whatever the amount of controls that you want to keep in a car, that is up to you, rather up to the smart city developer. And AXY is what? It is the GPS position, that is position which is fed by the GPS module. Now the information, that means the warning plus my coordinates, is fed to the reader repeater. Now in this case, it will be acting as a repeater and it will be sending this signal to the other cars which are following this vehicle A. Can you hear me?
Yes, sir, we can hear you.
Yes, yes, you are clearly audible. Please.
Okay. So I think there is someone is getting some problem that he or she is not being able to hear me. Okay. Screen is visible, no? So This warning signal along with the position will be given out by the reader repeater to the other cars. Now in this case it will be acting as a repeater, not a reader, because it is not sensing any signal, it is giving out some signal. Now why a repeater? Because a tag is having a very small antenna. Repeater is nothing but it is a signal booster, because you see in a vehicle to vehicle communication this signal has to be radiated in all the direction. Okay, now if a weak signal is divided in all the directions, then the signal will become weaker, and a vehicle B, which is in close range to vehicle A, will not be able to read that signal. So that is where repeater is included, which will be boosting the signal, and the signal will be sent out in every direction. Now in vehicle B, this repeater reader card is acting as a reader, because it is reading the signal which is given out by the tag. It is first sensing this warning code WC. Okay, so this and the whatever it is getting, it is feeding that thing to the memory through a middleware to the memory. Now in the memory it will decode this warning signal. Now keep one thing in mind, this thing should not vary from vehicle to vehicle. That means a particular protocol should be, a universal protocol should be maintained. That means 00 means I am taking a turn. It should be same for all the vehicles. 01 means I'll be suddenly pushing a brake. This should be same for all the vehicles. Okay, so this code, this warning code should be universal for everyone. So accordingly, the memory will detect the warning code. The memory will also decode the coordinates of that card. Okay, and then it will decode this message, and this message will be displayed to the driver in vehicle B. Let's see, a warning signal is given to you that the car which is in front of you will be taking a turn or will be hitting a brake and so on, and the position of that car is in this direction. That is easily decoded by the GPS model. And even you can put a system where this vehicle A can also be tracked by the vehicle B from that instant. Okay, so this is a part of vehicle to vehicle communication. What is another part of vehicle to vehicle communication? That is safety driving support system. Because see, in a smart city it is very, what should I say, it is very imperative to assume that accident should be less, and also to reduce the accidents the manual labor employed should also be less. Two things, I cannot compromise my manual labor to reduce the accidents. That means to reduce accidents I cannot use 20 traffic guards instead of 2 traffic guards. So how can I do this thing? See, here it is a crossing that is shown over here. This green car is moving in this direction, a forward direction. A scooter is coming from left to right, and some pedestrian and a cycle are coming from right to left. All of them are having RFID tag. Okay. Now, this entire area is covered by some low frequency signal generator. Okay, and this is a reader which is over here in this on this mast. There is a reader on this mast, if you can see. Now whenever any car or any pedestrian is entering in this region, now as if you remember, a low frequency system means it will be working as per Faraday's law of electromagnetic induction. Okay, so that means in the near field region. So whenever the cars or the pedestrians are entering in this region, in this low frequency signal region, then what will be happening? The tags in this car or in this scooter, the tags in this scooter will be all passive tags. Okay, so this low frequency signal generator will be sending out energy which will activate this tags. Once these tags are activated, the information about the car, about the coordinates of the cars or the pedestrians or this bicycle driver are given out by the tags to the reader. Okay, and now this reader is sending out the signals to everybody. Now there is a car over here which is going over here in the forward direction. Taking this, now take this example. This low frequency signal generator is there. It is nothing but some microwave device, some microwave vacuum tube device. This is generating some signal in the low frequency range. Now the passive tag in the scooter, in the bicycle, all are activated by using this low frequency signal in the near field. Once these tags are activated, the position of these tags, which can be the positions of these tags which can be decoded by the GPS model which is these are connected, the positions of these tags are fed to the reader. Okay, now the reader, after sensing the positions of this tag, the reader is also emanating this same information everywhere. Now there is a car which is moving in this direction. There is this information from the reader is intercepted by the tag of this car. Once the tag of this car intercepts this position, now one thing is again I want to tell you over here. This reader is connected to a controller. Okay, so once various tags are giving out some signals, and once the reader is reading the signals, it is sending all the signals to the controller via the middleware. Now the controller is decoding all the GPS positions, and it is giving the actual positions of the scooter and the bicycle with respect to this crossing. Suppose, and this same information is sent to the reader, which is giving out the information everywhere, and that is intercepted by the tag of this car. Now then, after intercepting this signal by the tag of the car and decoding the signal, what will it see? It will see that with respect to the crossing, a scooter is at 5 kilometer left, a pedestrian, a bicycle is at 3 meter right. The bicycle is approaching the crossing at say 15 kilometer per hour. The scooter is approaching the crossing at say 50 kilometer per hour. All these things will be visible to the to this car by virtue of the signal which is intercepted by this tag of the car from the repeater. And when it will see all the information, it can the driver of this car can modulate its direction of movement, or its brake or its accelerator functions accordingly. Okay, so this is the safety driving support system. It means that whenever a car is approaching any crossing, it will be given the information of other cars or bicycles or pedestrians which is approaching from other crossings or approaching from other bends which this car cannot see. Okay, so I am again repeating this system. There will be low frequency signal generator. Whenever some cars will be moving within this zone of the low frequency signal generator, the passive tags of these cars or these bicycles will be activated. Once the passive tags are activated, these will give the information of the location of this scooters and bicycles to the repeater through the GPS module, and also it will give the information of its speed to the repeater by the Doppler shift method. What will the repeater do? The repeater will collect all the information from all the cars which are entering this zone, and then it will send it to the controller through the middleware. The controller will decode the GPS information. It will also decode the speed by the Doppler calculation, and the position and the speed of each of the vehicle and pedestrian will be then given out by the reader in every direction. And once this signal is intercepted by any car, then the position and the velocity of other pedestrians or scooters or cycles will be clearly visible to this car due to the signal that is sent out by the reader, which is intercepted by this tag antenna of the car. So accordingly, after seeing this information, this car can modulate its speed, its direction of movement, and so on. Okay, so this is the what shall I say? This way, the safety driving can be done. So this is all about your RFID systems. What I want to say is that, lastly, vehicle management using RFID is a very open field of research. Very open field. There are numerous challenges. Some of the challenges that I can right now tell you are that designing exactly circular polarized antennas for readers or omnidirectional antennas for tags, matching the antenna network with the semiconductor network, good matching, because till now research is going on of how to achieve perfect between a tag and a semiconductor chip, that too in the gigahertz range, because in vehicular RFID system it will be working in the gigahertz range. Okay, then another thing is that your controller design part. Because if you see this safety driving also, because many times if you take this safety driving also, a tag is to be connected to a GPS module and that information has to be fed to the DPDR. So this interfacing of a tag with a GPS module is another important area of research. Then another important area of research is in the software domain, that is to develop different kinds of software platforms which can easily, for the middleware, which can easily decode the signal of the reader and uh, which can feed the that information to the tag from the reader. So these are the some open challenges that are in the market, and if you can come up with any solution, even a very small solution for RFID in vehicle management, that will be a very attractive one for your industry applications also, because industry is also stressing on this thing. As we are moving from manual to automatic, from wired to wireless, and from haphazard cities to smart cities, this RFID vehicle management is very prominently coming into the picture. So if possible, you can take up this thing as a research area. There are some papers available also. Okay, so this is from my end. If you have any question, then you can ask me any question of you, or if you want any suggestion for this RFID vehicle management, then you can ask me. I will try to help as much as I can. Okay, I hope there are no questions. So thank you for hearing me out. Thank you.
Thank you, Dr. Anumay, for addressing the lecture. I think this is a very different domain, so you can work on it if anyone is interested, and you are always free to write to him in case of any doubts and something more. So now I want to say something to you regarding whatever we are doing. Am I audible?
Yes, sir. Yes, sir.
Am I audible?
Yes, sir. We can hear you.
তুমি তোমার ভিডিও অফ করো অফ না অফ না Okay. So first, I want to tell something regarding tomorrow's session and furthermore tomorrow's test. Your test will be an MCQ type, which I will be taking online. I'll be sharing the link only over in this session. So it is expected that everyone should be there in the session tomorrow. I'll be sharing the link in the session. This is the one thing. Secondly, few of you have requested that there was some Deepavali is coming out and someone is moving around to done with the second half. So what I will do is that during my session, I will do the valedictory part also. So we will be finishing that by the first step itself. Is it clear?